department seminar. We have the illustrious Grant Petty presenting for us today, talking about shortcomings of Shannon entropy as a measure of information content. So a little bit about Grant. Got his PhD in 1990 from the University of Washington. Was a faculty member at Purdue from 1990 to 2000, and then at University of Wisconsin from 2000 to present. And he teaches undergraduate atmospheric thermodynamics, instruments and measurements, and a graduate atmospheric radiation and remote sensing course. Most of his career, he specialized in microwave radiative transfer and remote sensing, but has recently embarked on new adventures in drones and ultralight airplanes for airborne meteorological measurements.
Thank you. Well, there's not going to be any mention of aircraft of any kind in this talk, as you can probably tell from the title. This is probably, as I think John said, this may be the most arcane and abstract topic well, I think you said it's the one you've seen, the most arcane one you've seen or something.
Yeah, I used the word geeky, but arcane works.
Geeky works too, yeah. And it is an intimidating title. I'm going to try to make it more accessible than it sounds just from reading the title, which is very long and kind of formal. I did, in the course of preparing this talk, start to feel a little bit more militant about the topic. And so kind of a last minute change of the title is now, oops, how does that work?
Hit play.
Play.
Down the very bottom there. Yeah, here.
Well, what's going to happen now? Is it going to keep on going automatically? No. Okay, anyway, I changed it on the fatal question mark flaws of Shannon entropy as a measure of information content. And Shannon information content may be something that many of the people in the room have never even heard of, but is actually really becoming kind of a hot topic in satellite remote sensing as a way of measuring information. And so I'll get into that. I'll explain what it is. I'll explain what it does. I'll show examples, and then I'll show counterexamples of where I think it breaks down very seriously at times when you might want it to actually be telling you something. So first, some really basic background. We're accustomed to talking about data all the time. We may also speak of information, usually in a fairly informal sense. And the question is data the same as information? And the crude example that I'll use just to kind of set the stage for answering that question is that we can imagine a device that can remotely measure temperature with a pretty crappy precision of 10 degrees. And we can use it to measure the temperature at the location in the Amazon rainforest where the climatological, that is what we'll commonly call the expected or the a priori temperature, is known to be about 300 Kelvin with a standard deviation of 3 Kelvin. I just made these numbers up for illustration. I have no idea what the actual distribution is in the Amazon rainforest, but at least it allows us to illustrate the question. So if we make a measurement with this pretty bad instrument in a place where we already know that there isn't a whole lot of variability, let's say we get 298 plus or minus 10 Kelvin, that's the precision of our instrument. We could say in this case that the measurement is data, but it conveys no useful information. In other words, it may be data, but we don't actually know anything better about the environment we're looking at after making the measurement than we did before. So when we talk about information, we're really getting into the question, what do we know after the measurement that we didn't know before the measurement? How has it improved our understanding of the thing we're trying to measure? Now here's another example. Let's use the same device, same precision, to measure the temperature of a newly discovered exoplanet, where the prior expectation, based on whatever reasoning, is the temperature lies somewhere between 200 and 400 Kelvin. Well, now let's say we get the exact same measurement we got before of 298 Kelvin plus or minus 10. The measurement is data. It also provides information because it's greatly improved our knowledge of the temperature of that planet relative to our prior knowledge. So hopefully the distinction between data and information is now a bit clearer. So now to the more specific topic of the talk. Shannon, yeah.
Let's go back 2 slides back for the first example that you gave. You will, based on your prior information and that measurement, which is pretty crappy, admittedly pretty crappy,
Yeah.
you can still come up with a better estimate for the temperature of the Amazon with those 2 pieces of information.
Well, you could say that, yeah, that you're modifying, you could modify the temperature by tweaking the very, very small amount to account for this large uncertainty applied to that measurement. But it's not going to be much use. You're right.
It'll be a little bit, it'll be actually better than either one of those, you're doing
Right, especially, if your goal is to update a climatology, that single measurement with that precision is not gonna change it much, but you're right, you're getting something, but it's very, very little, it's negligible, really. And there's always information, but sometimes it's negligible and sometimes it's significant. And that's where the case I'm trying to make here. So coming back to Shannon, well, he's a guy who is known as a pioneer of information, or the father of information theory, based on a paper partly that he came out with in 1948 called A Mathematical Theory of Communication. Now, he was looking at cryptography and compression of data, transmission of data through data pipelines. He was mainly concerned with what is the theoretical maximum compressibility for transmission purposes of text messages, taking into account statistical relationships among the characters, maybe even words, and known redundancies. To take a highly oversimplified example, if Q in the English language is always followed by a U, you don't need to transmit both characters. You can reduce the size of the message by essentially encoding both as a single unit. That's how Shannon information content got, or Shannon entropy, as you'll see in a second here, was developed in that context. And a key concept in that theory is that there is an entropy, a statistical entropy associated with a set of events. So this is actually completely analogous to the entropy associated with the states of molecules in the gas and that kind of thing. It's actually very highly related mathematically. In fact, I think the same equation applies here. So formally, the entropy of a set of possible outcomes is given by H as a symbol for entropy, and it's basically the sum of the probabilities of the ith state times the logarithm base 2, if you choose to use that base, times the probability of pi, and you basically just calculate its probabilities for each state, do the sum, and you get H for that case. The information content of an event, like a message or a measurement, is essentially how does that H change relative to before you got the message. So, an example, and this is like the simplest possible example. Let's say you flip a coin and you cover it under your hand, so you don't know what the outcome is, and you want to determine what is the Shannon entropy of the state of the coin before you uncover it and take a look. Well, there's a 1/2 probability of it being heads, and of tails, you apply the base 2 logarithm, you multiply by 1/2 each case, you add it up, you get 1. And the usual way of expressing entropy in the Shannon context is in bits. That's why we use a base 2 logarithm. So we have 1 bit of entropy associated with that coin before we actually measure what the outcome is. Once we uncover the coin, we get 1 outcome. And so now you have 1 state with 100% possibility. You take the base 2 logarithm, you get 0, and so you've gone from an entropy of 1 bit to 0 bits, and the difference is 1 bit, and so you gained 1 bit of information as a consequence of making that measurement. And it makes sense. You've got a coin that can have a state of 0 or 1, so to speak, and when you measure it, you've essentially gained 1 bit of information. Now, there's a continuous generalization of the Shannon entropy that I think Shannon himself did not envision, and I'm not sure if he ever really weighed in on whether it's valid or not, but it's actually used to essentially determine the entropy of a continuous PDF, probability distribution of a variable like x. And it really generalizes in a fairly obvious way. You're still taking the product of probabilities in the log base 2 of the probabilities, integrating over all possible x, you get the entropy of the distribution. There's some subtleties in this generalization that pertain to non-uniqueness and coordinate choices, but otherwise it makes sense. Yeah.
I'm just geeking out here. So that H looks kind of like, the way it's formulated, like the expected value of log P, log base 2 of P.
That's exactly what it is, yeah.
So that's the relationship between entropy and, it's like an expectation?
Well, that is, the way it's written, it is, you can interpret that as an expectation value of the base 2 logarithm of the expectation at each value of x. I'm not sure how to go beyond that in terms of interpreting it, but that is what the mathematics say. Okay.
Just curious, but.
So now we can generalize and say, well, we can consider the Shannon information content of a measurement that changes the PDF of x relative to prior knowledge. And the context for us in meteorology is often the climatology. The climatology gives us a certain statistical distribution of a value like temperature, wherever you are. And if your measurement gives you a new PDF, which has a different shape, probably a different width, then the change in that PDF is reflecting the measurement that was made. And the question is, can we quantify that in terms of Shannon information content? And of course you can if you just apply the equations. If you have a prior PDF that is P of X, and you have a posterior Q of X, then all you're going to do is calculate the Shannon entropy for each of these distributions separately, take the difference, and that delta H is now the Shannon information content associated with that change in the PDF. So the idea here is that a measurement that reduces the Shannon entropy of the PDF is conventionally assumed to convey positive information. And the first time this was applied in remote sensing, to the best of my knowledge, was by Peck in 1974. And this is kind of characteristic of the way it's been used in a lot of remote sensing literature to follow. The idea is, in this case, he was retrieving a vector of temperatures, like a temperature profile. And the prior and posterior PDFs in this case were assumed to be Gaussian. And the idea here is you start by finding the single channel in your sensor that is going to minimize, or is going to maximize, the reduction in the entropy of the multidimensional PDF relative to climatology. So you're looking for that first channel that gives you the most information, and then you look for the next wavelength or channel that will do the same thing with what's left over, and you repeat until you have as many channels as you can afford to put on your satellite or to process with your algorithm. Now, a lot of authors have gone on to do essentially the same thing in slightly different contexts. I'm not going to list them all. I've got Rodder's 2000 in bold here because he actually wrote a very influential textbook on inverse methods in remote sensing. And that textbook, I think, has influenced a lot of people's thinking about the value of Shannon information content as a way of understanding the inverse problem. And I'm one of them. I was influenced by that, and I was a strong believer in Shannon information content for quite a while, until I essentially hit a situation where it no longer worked for me, and I had to look at why. So there's two exceptions to the Gaussian assumption. Posselt and Coddington have some relatively recent papers that didn't use the Gaussian assumption, but they applied it to discretized prior and posterior PDFs. Now, I don't really know the details of what's in there. I haven't looked at those papers in a while, but just to know that most people have been doing it in a Gaussian context. Now, the thing about Gaussian statistics is that, let's say your prior and posterior PDFs are scalars. Let's say your X is a scalar. You're not getting a profile, you're just getting a single variable like the temperature of the surface or something. Then the Shannon information content, delta H, distills down to a really simple relationship. It's simply the log base 2 of the ratio of the posterior and the prior standard deviation. So if you get a factor of 2 reduction in the width of that spectrum, or that PDF, you get 1 bit of information. If you get a factor of 4 reduction, you get 2 bits of information out of it. If you're dealing with a multidimensional problem, like a profile retrieval, so X is not a scalar, but rather an n-tuple or a vector, with covariance S, it's a little more complicated, but the same basic idea. You've got the determinant of the prior covariance divided by the determinant of the posterior covariance, and you take the base 2 logarithm of that, and you get basically something analogous to this up here. Now, what do those determinants mean? They're really just a measure of the hyperdimensional volume of the ellipsoid represented by the covariance. So you have a covariance in, say, 2-dimensional space. You get an ellipse, which essentially encompasses all your points, or many of your points. You go to 3 dimensions, a 3-dimensional ellipse, and the determinant basically gives you the volume of that, and the ratio of the volumes is basically telling you how much information you're gaining in the Shannon sense. Okay, well, that's all well and good, and that's how it's been used in a lot of papers that use the Gaussian assumption. My question, it's a question for debate, because I don't actually know the answer to this. There might be an angle to this that I'm not seeing. If the information content can be expressed entirely in terms of reduction of the error covariance of X, do we really need Shannon entropy at all, or can we just talk about the reduction in the variance? Can we say, well, we reduced the variance by a factor of 2, and maybe our goal is to maximize the reduction in the variance in our retrieval? What additional insights are we getting from Shannon? There may be an answer to that I'm not seeing. I just don't see it. So the central propositions of this talk are that the whole idea of Shannon information content, well, first of all, the first point is it really hasn't been looked at in the context of non-Gaussian, arbitrary non-Gaussian prior and posterior PDFs. I'm not aware of anybody having really examined how applicable Shannon information content is in the case of retrievals where you have non-Gaussian prior and posterior PDFs. Well, that leads to another issue, and that is it's very hard to even talk about prior and posterior PDFs that are arbitrary without talking about Bayesian retrieval methods, because as far as I know, Bayesian retrieval methodology is really the only way to start with a prior arbitrary distribution of your value, your variable that you're retrieving, and convert it to a posterior distribution that's not just an assumed Gaussian with a centroid and a spread. So now there's a few people out there that have things that they call Bayesian algorithms. I'm a little bit restrictive in what I call a Bayesian retrieval, because I'm referring to one that's based on explicit application of Bayes' theorem, returning a full posterior PDF of X rather than just a best estimate of the value, like the mean or the expected value in the error variance. So we're trying to be very general, and it's very hard to do that in most cases. But that's really, I think, the only way to even get at things like arbitrary prior and posterior PDFs in most cases. Now, there's an example. Christine Chu, who worked with me as a PhD student in the early 2000s, right when I came here, actually did her dissertation on an explicit application of Bayes' theorem to continuous representations of PDFs. She's now recently a faculty member at CSU, which I just found out about a couple weeks ago. But that's one of the few cases. So the final main proposition of this talk is that even relatively simple experiments with Shannon entropy applied to non-Gaussian distributions reveal that the Shannon information content may be far less meaningful in context remote sensing measurements than is commonly assumed, and was assumed by me until I actually was forced to confront a problem. So let me do a little side trip, a little primer on Bayesian retrieval, because some of you may have heard the term, but don't know what it is. And it's actually not as difficult to understand or visualize as you might assume if you simply look at the way it's usually written mathematically. So Bayesian retrieval is a conceptual framework for solving an inverse problem when the forward problem can be characterized either theoretically or usually empirically in terms of a climatological joint probability distribution, P of x, y, where x is the thing you're trying to retrieve, typically y is typically the observable, and they can be either vectors or scalars. We're going to keep it in scalar space just to make it easy to look at and understand. And it works like this. First, Bayes' theorem is something that is usually presented to people kind of as a fait accompli without really saying where it comes from, but it really is not hard to get from just a few basic relationships. And this also gives me an opportunity to do some notation. So on the left here, we have the joint PDF of x and y. That's basically the thing you'd have to integrate over both x and y to get 1, which basically says what is the relative probability of each possible pair of x and y. Well, that turns out to be proportional to the probability of just x, that's the marginal distribution of x, multiplied by the probability of y given a particular value of x. It's also, conversely, proportional to the marginal probability of y times the probability of x given a particular value of y. So that's really what those are just basic relationships. These proportionalities can be turned into equalities simply by supplying the normalization constants you need to have a PDF that integrates to 1. That's all there really is to get that to an exact statement. So in the following, I'm assuming that P of x and y fully accounts for a whole bunch of things. It's all thrown in one pot. The direct physical dependence of y on x, that's what you might model. The climatological PDF of x, that's how the thing that y depends on varies climatologically, statistically. The physical dependence of y on variables other than x that aren't necessarily modeled but are in there and change the value of y. The climatological joint PDF of those other variables with each other and with x. There's a lot of implicit relationships and correlations that are potentially built into that, and even the measurement area in the observations of y. In short, P of x and y is literally what you get if you just make a lot of real-world matchups between, say, a satellite and a given variable, collect millions and millions of them, and use them to construct the statistical distribution of x and y. Everybody follow that? Okay. So for any particular value of y, the probability of y is a constant. So you essentially can get that the probability of x given y, this is the retrieval right here. We're saying our observation is y, what's the probability distribution of x that goes with that y? Be written in terms of that product right there. If you normalize that properly, you get that the probability of x given y is just that same thing with the normalization down below. It's just the integral over the same expression, so you get 1 as the normalized area under the curve. So the thing to keep in mind is that thing right there can be thought of as just p of x and y with maybe a slightly different normalization constant. So it's a lot easier to understand how this works if you look at it graphically. And so here's what I'm going to try to do. This is a fictitious joint PDF that I created. And that grayness basically represents how probably something is. You can think of it as like a scatter plot of such a large number of points that all this blurs together into one cloud. And x is again is our thing that we're trying to retrieve. Y is our thing that we would observe with the satellite. And the joint distribution is given by this cloud. It basically shows what's the statistical relationship between x and y. Well, if we look at the prior distribution of x, in other words, what's the climatology of x, we're basically just integrating this thing vertically at each point, and we get this distribution. It looks fairly Gaussian. It turns out not to be exactly Gaussian in this case, but close enough. But you can see this is where you would expect the range of x to fall. And you can do the same thing integrating for each value of y and get a y distribution that shows the marginal distribution of just y. But it's not terribly interesting for our purposes here. So now what happens if you make a specific observation of y? Let's say it's radiance, and let's say x is temperature. Then that observation of y defines a line which intersects this cloud of points. And once you intersect that cloud of points or that PDF, that joint PDF, you get a new distribution of the x's which are consistent with that value of y. Does it make sense? Mm-hmm. So this is the new PDF, the posterior PDF of x, relative to the prior, which was the climatological distribution. And the implication here is that by making a measurement of y, we learn more about x in a specific instance than we knew from climatology. Now, just a couple of caveats, which are not kind of a side topic in a way, but we almost never have a continuous functional distribution of px and y to work with. Again, Chu and Petty is the only exception I'm aware of, unless you're working with Gaussian distributions. Instead, we typically rely on an empirical database that matches between x and y to represent indirectly that joint distribution. And typically what you do if you have enough points is you make like a histogram, a bivariate histogram or a multivariate histogram, and treat it as a lookup table, and you're basically dialing into that lookup table with your y to get the appropriate set of entries to give you the posterior distribution of x. That's how it's done in practice. That's how it's done with my microwave rain rate retrieval algorithm. Especially in high dimensional observation space, like a 9-channel satellite sensor. It's a 9-dimensional space, an observation space. It's really, really hard to get enough matchups to actually densely populate the representation of that joint distribution. So when you start working with multi-channel observations, if you try to work with them in the native channel space, doing this generation histograms and all that turns out to be very hard because you need billions and billions of points to get anything remotely usable. Now in this case, just to use a scalar illustration, here's the original continuous PDF. That's the idealized PDF that we assume applies to the entire globe over all time or whatever. Here might be what you get in the sense of actual empirical matchups. It's a fairly sparse sampling of that PDF. You kind of get the shape of it. You have some gaps. You have a couple up here. These were actually generated from that PDF, so this is actually a realistic representation of how you sample that smooth PDF and get something you might actually be able to measure through mashups, right? And you see it's not a great representation. Now, take away that original PDF. Now we just have our empirical matchup data. And now you take your observation of y, and what's the posterior PDF from that? It's not really obvious. So what people have tended to do, and I say people in quotes, I know specific cases where this is being done, what they do instead is they simply look at some delta above and below that line, and they get all the points that are within that delta. They average them together, and they call that the retrieval. Okay, it's not really Bayesian anymore. You're not getting a PDF out. That's why I make that distinction between a true Bayesian method and one where you're basically you're doing the sample matching. You're just going into a database and looking for the ones that are closest to your observation. So anyway, this is a complexity which would take me a whole lecture in its own right just to explain how we deal with it. But to cut to the chase, we came out with a paper in 2013 where we describe an algorithm that does actually address the dimensionality problem. We get from 9 dimensions down to 3. We're able to densely populate the PDF. We're able to actually do PDF retrievals. And so not only are we getting an estimate of the expected value of the rain rate, we're also getting a discretized posterior PDF of the rain rate for that scene. I'm not aware of any other rain rate retrieval anyway that does that. It relies on up to 3 pseudo-channels derived from the original 9-channel TB data. If you utilize 0 of those pseudo-channels in your retrieval, what you get back is climatology. So you can actually look at what the climatology is for a given situation, and then you can specifically look at how does that PDF change as you throw additional pseudo-channels into the mix. How does each one refine the PDF relative to what we knew before? It's going to change the mean rain rate, and it will possibly change the shape of the PDF a little bit as well. And it seemed like an ideal situation to examine information content. Say, we're starting with climatology, we get our first principal, our first pseudo-channel. How much information is the first channel providing, according to Shannon, in a given situation? And what happens if we add the second and third? Does that further improve the solution? So I had Khalid and here's an example of what that algorithm does. Here's the raw channel brightness temperatures for just 4 of the 9 channels, just to show we got real data here with 4 channels. We turn a crank, grind all 9 channels into these pseudo channels, and magically out comes something I don't think I've seen anywhere before, where we have conditional probabilities of rain exceeding various thresholds. It's basically we're just truncating, we're truncating the PDF with different thresholds and seeing what's the probability of rain greater than 0.01 millimeters per hour. Well, this white is basically essentially 100%, right? So everywhere within a white, we know we got 100% chance of the rain being at least 0.01, and a few outlying areas where, well, maybe it's only a 50% chance. Go to a higher threshold, 0.1, the area becomes slightly smaller, but we still have a very high probability of rain greater than 0.1 throughout the white areas. Go to the next threshold, 1 millimeter per hour. It's looking a little bit more restricted now. We're losing a lot of the outlying stuff. The probabilities may be down towards 0 for areas where we previously thought we had light rain. We're starting to see the rain bands. And if we go up to greater than 10 millimeters per hour, we start picking out just very few areas where the probability is like 50% or greater, in a few cases approaching 100% in these little white spots right there. So the point is, we're actually able to get these PDFs. For every pixel, we're getting a PDF of rain rate that we can then convert to these values. So, the case of cognitive dissonance. This is where I began the first question. Shannon. Following the publication of the algorithm, I had Cub go look at the Shannon information content of the added pseudo-channels in various cases. We wanted to understand what are they actually adding. We expected, just because this is kind of the lore of our field, that Shannon information content would either be 0 or greater than 0. If it's 0, the measurement's not adding any knowledge to the situation. If it's greater than 0, it is, right? But what we found right off the bat was that even the first pseudo-channel, the one most responsible for the final result, yielded large negative Shannon information content. And that was like, having to rethink how the world works, because I was so conditioned, mostly by my own thinking, to think that Shannon information content was this wonderful way of viewing information. How could it ever be negative? Well, some thought experiments began to reveal how Shannon information content isn't quite what we thought it was. And so I constructed a thought experiment that goes like this. There's a Jennifer, maybe she's the boss in her office somewhere. She gets a note from her secretary Jill that a call was received from Jim and that she should call back. It seems like information, but this is kind of the base case here, right? She finds the note ambiguous because 70% of her past calls were from Jim, were from her supplier Jim Smith, 20% were from Jim Johnson, and the remaining 10% were distributed equally among 10 other Jims working in her large organization. So we got basically prior probabilities of 70%, 20%, and 10 times 1% for the remaining. And you can calculate the Shannon entropy of that case, and it's a relatively low entropy of 1.5 bits, reflecting the high probability that the caller was Jim Smith, because that was 70% of the possible outcomes, right? So she wants to clarify the situation, and so she gives a follow-up question. She asks Jennifer Jill the last name of the caller. And Jill says she doesn't know, is she sure it wasn't Jim Smith? Okay, so with that response, she's radically changed the statistical landscape, eliminating the most likely caller. What is the formal information content of her answer? Well, you just have to look at the posterior PDF. So new probabilities can be calculated easily at 66.7 for Jim Johnson. Jim Smith is no longer in there, 3.3% each for the remaining 10. And the new Shannon entropy is 3.3 bits, a larger value, an increase of 1.8 bits implying negative information content. So if you like Shannon information content, you have to contend with the fact that it may be negative in situations where you objectively think, or maybe subjectively think, you're getting actual useful information. Don't call Jim Smith. All right, so
Grant, I thought when the entropy went up, when delta H goes up, that's good for your information content.
No.
It's the other way around.
so entropy is basically a measure of diffuseness of your PDF.
So you made it
And
more
if you
diffuse.
make it more concentrated and more
Yeah.
focused, so you have a better idea of your answer, then the entropy goes down, information content.
Oh, so I remembered the original subtraction the wrong way. Okay.
Yeah, well, there's a minus sign in front of the original
Yeah, okay.
equation.
But the total number of possibilities has gone down.
Right.
But the likelihood of any of those possibilities has gone, you've
Gone up.
the likelihood of, initially the likelihood was very focused.
Right, and you tripled the likelihood of one of those 10 extra Jims, right? And you eliminated the one you thought was most likely. So you vastly reshaped the distribution of probabilities. And the question is, why does Shannon information content give us a negative result for that? So
That's interesting.
now back to the real world truth. This is the experiment that I did, that I kind of used to, as a way to also look at what happens with our rain rate retrievals. Our prior PDF of rain rate, due to climatology, is that most of them are 0, right? Usually it's not raining at most points on the Earth's surface most of the time, right? So the most likely value is 0. And there's only a very slight chance that maybe your satellite technique or your microwave radiances don't really see maybe some little tiny shower in there. So you've got some small values for higher rain rates, up to about 0.5, and it kind of falls off together. You make your measurement, and you rule out, effectively, a 0 rain rate, or at least you knock it probably down to a much smaller value. And now you have a distribution of possible rain rates that looks like that. It's peaked. It's got a mean that's somewhere up around probably 0.5 millimeters per hour there. You've got a fairly broad distribution of possibilities because it's not a precise measurement system. And this is exactly analogous to the case I just gave with Jennifer and Jill. We've knocked out the most probable case, and we've wound up with a distribution which we believe is a significant improvement over what we had from climatology. But it's got a broader distribution and higher entropy. So my claim is basically, and this might be a little contentious, I don't know, the change in Shannon entropy is simply not relevant to the question of whether the satellite retrieval improved our knowledge of the rain rate. Maybe some of you have seen this meme floating around the internet. Maybe not. It's that meme is used for a lot of different other things where, never mind. All right, well, to illustrate the problem further, let's go ahead and look at idealized Bayesian retrievals from idealized constructed continuous joint PDFs. First, a boring Gaussian case. Here we got a Gaussian PDF in X and Y. It's got a pretty good correlation between X and Y, that's why it's tilted. You can look at the prior distribution of X, which is basically this curve right here. You're basically just integrating this thing vertically to get that curve right there. You get a value of Y, your observation, which cuts through that PDF right here. And now you basically, by sampling that PDF right across that line right there, you get this new PDF, which is very sharply peaked. You've got a revised value of X that differs from the climatological mean. You got a narrower distribution, your variance is down, and you can look at that and go, wow, I got information from that. The prior PDF is, or the prior Q, the prior H is 4.47, the posterior is 3.05. We gained 1.42 bits of information according to the Shannon definition. So it seems very logical, it makes sense. And it's important to understand that as long as it's Gaussian, it can never be negative, because let's say that this is completely uncorrelated between Y and X. You still have an ellipse, but it'd be horizontal, right? And no matter where you slice it with Y, you're gonna get the same climatological PDF back out again that you started out with. In that case, the Shannon information content is 0, the variance hasn't changed, your estimate of X hasn't changed, and you can legitimately say that your observation of Y didn't add information to your knowledge of X. All right, so in the Gaussian case, if Y is correlated with X, then observation of Y always yields a revised estimate of the expectation of value of X with a reduced variance to sigma X, and the Shannon information content is always greater than 0. If it's uncorrelated, well, you'll get an unchanged prior or posterior PDF. The Shannon information content is 0. The SIC can't be negative, and I guess most importantly in terms of its potential meaningfulness, it's uniquely related to the error variance. You can't decouple the error variance from the entropy in the Gaussian case. It doesn't contain unique information. So these are the rules which I had kind of internalized after reading various books and papers about it, and came to expect that this is all generally true for all measurements in all situations. Now here's an example of where things start to really break down if you look at them with the right examples. It's a non-Gaussian case, highly non-Gaussian. This is a Gaussian right here. Here's a bimodal Gaussian, same distribution, right? Same area under the curve, same entropy, 4.0 in both cases. Wildly different variances. Variance of 4.0 in this case, so the spread of that is 4.0 units. The variance of, actually not the variance, it's the standard deviation. The square of that would be the variance. The standard deviation for this distribution is almost 4 times larger, but the same Shannon entropy. If you compared these two distributions, if you called one the prior and the other one the posterior, you'd get no difference. It would not indicate that there was any informational difference obtained by going from one to the other. Entropy does not care about variance, and yet variance is what we normally care about when we characterize the error in measurements. Here's another example, a contrived non-Gaussian case. I got a very high concentration of points down here, and then kind of a broadening Gaussian distribution as you go up to higher values of Y, and I kind of scoot everything over. And you can start off with the prior distribution right here, which is dominated by most of these points right here. That's why it's fairly narrow. And you get an observation of Y. You get a new distribution here. Your posterior distribution is significantly modified. You went from an estimate of X of around, whatever that is, 10 to close to 30, but it's got a larger variance. It's got a lower peak, broader spread. The prior H is almost 4. The posterior H is almost 5. You're getting a negative information content of 1 unit here, almost 1 unit, as you go from your climatology to your legitimate estimate of the value and distribution of X in a specific case. There's something wrong here. Suddenly things no longer seem quite so neat and tidy. So a retrieval can correctly yield a markedly revised estimate of the mean value or the expected value of X relative to climatology while exhibiting both an increase in error variance and negative Shannon information content. And you saw that in the example of my PDF of rain rates. And my argument here is that in such cases, neither the Shannon entropy nor even the variance in some cases are reliable indicators of the information content of the observation. So returning to that introductory example, we're back to our device that measures temperature with a precision of 10 Kelvin. This is the same example I showed at the beginning. We use it to measure the temperature location in the Amazon. The climatology is 300 plus or minus 3. We get a measurement of 298 plus or minus this terrible 10 Kelvin precision. And I argued in that case it conveys no useful information. But let's modify that a little bit, but not quite the way you might think. Let's take the same measurement in the same place. Amazon, 300 plus or minus 3 is the climatology. Precision of the instrument is still 10. Now we get a measurement of 270 Kelvin plus or minus 10. Same poor precision, but we suddenly have a result here which falls pretty well outside the climatological distribution of T in the rainforest. So although the precision of the measurement is the same as we saw in the earlier example, it now tells us something unusual is going on. It's not consistent with long-term climatology. And it might even be instrument error, but it's something different. In this case, the argument I'm making is that the surprisal factor, which doesn't necessarily have to do with the spread, should be counted as information. An event previously assumed to be rare suddenly became far more likely. So, conclusions. I thought I was going to have trouble getting into the time. I guess not. Maybe I went too fast. In the purely Gaussian retrieval problem, Shannon information content is uniquely related to changes of area variance, and therefore, arguably, debatably, controversially maybe, provides no additional insight. In general, the Shannon information content is oblivious to the variance in your prior and posterior PDF. It doesn't know about spread, it doesn't care about spread. And I forgot to mention this, but, or to remind you of this, but this was originally constructed in the context of message transmission. And the distributions in this case consisted of things like letters and words, right? So if you are predicting a character that's going to come in your next, as the next character in your stream, and you're predicting it to be an A, but it turns out to be a B, well, it's wrong. If it's a Z, it's also wrong, but it's no more wrong than B was. There's no sense of spread or variance in characters, right? And in messages. So variance is something that we encounter when we talk about measurements of continuous variables, but it is not terribly relevant. Well, it's not even accounted for in the Shannon information content of the Shannon entropy. And in some non-Gaussian problems, just to recap here, even a change of variance may not be a reliable indicator of retrieval quality. Sometimes you can get an improved estimate of X and still have a larger sigma X associated with that than you had from climatology. I guess I kind of went into this already, forgot this was coming. So I already said all that. There's something called the Kullback-Leibler divergence, which I didn't talk about today for reasons of time. And it's also known in the atmospheric science literature as relative entropy. It's always positive for any change in PDF. So if you have a change in PDF like we showed earlier, it's going to give you a positive value, but it still doesn't know anything about variance. And so it's still a questionable value for characterizing the quality of remote sensing measurements. I think that's it. Just a couple of acknowledgements. Again, Kali was the first one to start looking at this as part of his master's thesis. I kind of took that as a starting point to re-examine the whole concept. Tristan entertained some conversations in his office and pointed me to some literature he was familiar with, and it was funded by the PMM program at NASA. And then here's some selected references that relate to at least the stuff we've done in this area. So I guess I can take questions now. Thank you very much. John.
Are there leading, this is really interesting, Grant, and well presented. I think I came in not knowing if I'd understand any of it, and you helped me understand a lot of it conceptually. Thanks. Are there leading ways that you can measure characteristics of PDFs? So mean is obviously one. How would you then characterize
kurtosis?
Yeah, what about, and I don't know enough about this, but if you go, like some of your shop peaks, you have a mean that's really quite restricted, and then there's not much variance around that.
Right.
Where along that vertical peak line should you measure the variance to be consistent with one comparison to another? Because it seems like all these methods just, maybe it's because you can't do that easily with PDFs to compare the variance to various distributions, so that they all neglect
The last part of your question I didn't quite follow. So if you have a PDF, it's basically giving the relative frequency of occurrence at values of X along the axis,
Right.
So it's narrowly peaked, then you've got a high probability of X being in this narrow zone,
Right.
and a low probability outside that.
Right.
So that would be measured by the standard deviation of the variance.
Yep.
If you cared about it being non-Gaussian, you might look at the kurtosis.
Mm-hmm.
If you cared about the peak and not the mean, you might look at the mode.
Yep.
You might look at the median, which divides into equal quantities on either side.
So taking any of those other measures of these distributions, can you imagine a way in which you can formulate a new measure of entropy or something like the last one you said that takes those into account? Or do these methods
That would be
just
for smart
systematically
people.
exclude them?
That would be for smart people. I don't know how to do that.
Yeah.
I mean, the essence of this talk was my finding that a method and a conceptual framework that I thought made a lot of sense. Suddenly didn't make a lot of sense if I took a closer look in the case of non-Gaussian distributions. I have no idea what to say now as a possible way to go back to looking at information content in a way that is more, I guess, well-grounded
Yeah, that takes
in
care of those
non-Gaussian statistics.
Yeah, it's
But
really
it's a good question. And I think fundamentally in remote sensing, you have to say, what is it you're trying to optimize? Are you trying to optimize the variance? Are you trying to find the mode of the distribution? What is it you're trying to actually retrieve? And then I guess your measure of whatever quality it is has to be tied to that goal. Dan?
It seems to me that the issue here is that the definition of information is very different than the definition of distance from the actual answer.
Right.
And so the continuous, I mean, your example of a continuous distribution is important there. As you're pointing out, the increase in the entropy, even though you have a better estimate of the true mean, like your example of rainfall, for example, you actually have, even though you have a better estimate of the conditional mean in this case, you've greatly increased you've greatly decreased the amount of information that you have pertaining to that particular problem, because you now have so many more likely choices by having a conditional PDF. And so you actually have much less information now about which of those choices is correct. And so what I'm wondering here is...
Okay, but let me stop you there, because my bins are arbitrary here.
It doesn't matter, yeah.
I could throw these all into one bin and just say no rain and rain.
Mhm.
And you still get an increase in entropy when you get to this value of about 0.3 something for the no rain and 0.8 for the rain. So in other words, no matter how you slice this problem up, the Shannon definition of information.
Right, but initially though, the information is again, I think there's a difference between the information and then what you're trying to measure. I'm trying to conceptualize this in my head at the same time as you're presenting this. I've never seen this before, but so even in that case, you have an increase in entropy, even if there's only one other bin.
Yeah, in that specific case, yeah. Because you go from one highly likely possibility with one relatively unlikely possibility to two possibilities which are closer to being the same. Kind of approaching the non-flipped coin for the coin you haven't looked at yet.
Right, because but again, you're reducing initially because you only have a certain amount of information, right? You don't have that additional piece of information, so maybe the issue is that it'd be interesting to carry out this Bayesian process within the integral of the entropy to find out whether or not, have you actually carried that through to find out whether or not there's something fundamental about the structure of the Gaussian distribution versus other distributions that necessarily give you that reduction in entropy?
Well, I mean, I think there's lots of cases where it could be non-Gaussian and still give you the reduction in entropy. I think that the main thing that the Gaussian distribution has going for it is it only has two free parameters. And so you don't have a lot of room to...
Well, it's also single peaked, and it doesn't you don't end up with a broader spread
Right,
on any of the conditional.
right.
Right, the conditional variance is the same no matter what your observation is. 1 minus rho squared.
Oh, okay,
Root 1
sure.
minus
Yeah,
rho squared.
yeah, sure, sure, yeah.
I just wonder whether or not whether this gets to just a fundamental difference in what we think information is.
I think that's what I'm saying.
Yeah.
I think what I'm saying is the information scientists who deal with information in a certain context are using it in a way which for them is completely appropriate.
Yeah.
And for us, it may be inappropriate. I mean, in this case right here, we started with a climatology where we assume, we presume there's no rain or location. We get our microwave observation. Suddenly, we're saying it's 70% likely that there's rain occurring there, and the likely distribution of rain rates here with the expectation value around 0.3. It's not, if you can think of that 0.3 as being the value plus error bars, which go to either side, so you're actually getting a retrieved rain rate with error bars out of that distribution there.
And there's now a far more larger set of likely possibilities than there was. The likelihood of those possibilities is much larger.
Right. You've basically gone from what was,
Yeah.
by assumption, a rare event and turned it into
Yeah.
high probability, and you've taken what you thought was your most likely event and made it unlikely. So you've vastly reshaped the probability distribution. And again, the argument is that's information when you change your PDF.
Yeah.
No matter how you change it, it's different. And if you trust the later one more than you trusted the earlier one, then your information is improved.
I wonder what, sorry, Dom, the last thing I'll say is I wonder whether, I mean, in the definition of Shannon entropy, recognizing that it is an expectation of the log of something that looks kind of like, whether you use a likelihood function or something in there to infer whether or not there's, you know, to get to something more general.
There might be something there that's beyond my pay grade, or my ability to look it up myself, but I'd love to have more input from somebody as to what might actually be going on. But I think my conclusion is really basic, and that is Shannon information content doesn't mean what you think it means. And it works fine in a Gaussian case, but it doesn't tell you anything new in a Gaussian case either. As soon as you drop the Gaussian requirement, suddenly it means nothing that is meaningful to us, or potentially means nothing to us. That's it. And this might make some people mad, because a lot of people have published papers using Shannon information theory, and I'm not sure if they're going to like this. Or if they might actually come up with some arguments why I'm not looking at it right, which is also possible. Any other questions? Thank you very much.